Okay, next we move on to a very important theorem or a property called nested intervals property. So this is called nested intervals property. This is very important as this has been asked in many university examinations. So this is a statement. So this is a named theorem. So you will have to learn the both the statement and the proof. Okay. So if in equal to a and bn, where n belong to natural numbers n, is a nested sequence of if in, a and bn belong to n is a nested sequence of closed bounded intervals. Closed bounded intervals, then there exists a number eta, okay, it's a real number such that eta belongs to in for every n belong to n. So what does the statement say? So here we have a nested sequence of intervals, that is we have I1, which is the biggest interval. I1 will contain I2, I2 will contain I3, etc, etc, etc. So we have a nested sequence of intervals. So if we have such a nested sequence of intervals, this theorem states that if the sequence is closed intervals, okay, it should be a sequence of closed and bound intervals. If that is the case, then this theorem states that we can always find a number which is common to every n. That is, we can find an eta such that eta is there in I1, eta is there in I2, eta is there in I3, eta is there in I4, in any n, for n corresponding to any positive integer n or natural number n, this eta will be there in any n. It will be there in the 100th interval, it will be there in the 1000th interval. So every interval I1, I2, etc., everything will contain at least one common member called eta. This is what the theorem says. So here is the proof. Let's see the proof. Okay. So since the intervals are nested, so what does it mean? Every interval will be contained in the preceding interval. I3 will be contained in I2, I2 will be contained in I1. That means I1 is the biggest interval, okay? So since the intervals are nested, comma, we have in will be contained in I1 for every n belong to set for natural numbers. I2 will be contained in I1. I3 is contained in I2, but I2 is contained in I1, therefore I3 is contained in I1. So I1 is the biggest one, okay? So this is true for every n, okay? So or diagrammatically, if you want to see, here you have an, bn, that is contained in I1 means here you will be having a1 and b1. This is true for every n belong to for natural numbers. This is what I say. Okay. So just see, if n is equal to 2, then a2 will be here, b2 will be here, and b1 is here. If n is 3, a3, b3, b1, a4, b4, b1, a5, b5, b1, a6, b6, b1. Okay. That means, now see, this implies what? A1 is less than b1, a2 is less than b1, a3 less than b1. So at any cost, b1 will form as an upper bound for the set of all an's. Okay. So this implies what? This implies the set an, n belong to n, is bounded above. So this set is bounded above. This set is bounded above by b1, since an is less than b1 for every n belong to n. Okay. Therefore, the set is bounded above by V1. Therefore, by supremum property, what exists? Supremum of A in sup of the set A and n belong to n exists. Okay, so let eta is equal to supremum of AN's, where n is a natural number. Okay, so eta is the supremum of all these elements. So this implies AN will be less than or equal to eta for every n belong to n. Okay, so one part is okay. Now we will prove that. Secondly, we'll prove that eta is less than or equal to Bn for every n belong to n. Okay, so this is what we are going to prove. Okay, and in order to prove this, you have to consider two cases. Okay, just see. So we have two cases. So case one. Okay, case one has okay, if n is less than or equal to k, where n and k are both natural numbers. Okay, see, this is a nested sequence of intervals. So what did we see there? It was like this. Okay, I1 will be containing I2, will be containing I3, etc., etc. You see, as the suffix 1, 2, 3 increases, the size of the interval is actually getting decreases. It is actually getting decreased, because I1 is the biggest one, I2, the suffix is 2, but I2 is much smaller than I1. Okay, and what about I3? Again, the index increases, but the size has a tendency to decrease, because it will be smaller than I2. Okay, or at least equal to. So as the suffix increases, so when you compare 1 and 3, that means I3 is smaller and I1 is bigger. So what about 3 and 5? I5 will be smaller, I3 is bigger. What about 10 and 20? I10 will be bigger, I20 will be smaller. Okay, so similarly, based on such an understanding, we have to make some assessments over here. You see, n is less than or equal to k, that means k is bigger and n is smaller. So sequence in being a nested sequence, we have what here, k is bigger. Okay, we have in will be containing ik. Now what does it mean? What is in? In is an, bn, that will be containing ik. What is ik? That is ak comma bk. Therefore we can, in this case, we can always write what? ak less than or equal to bk, and bk less than or equal to bn. Okay, so we can write such a statement. Now case 2. Now what does case 2 says? If n is greater than k, here we got n less than or equal to k, and here we consider n greater than k. Now see, here n is bigger and k is smaller. Okay, therefore, as we argued previously, we can say that here also, here in and ik, how will you compare these two? N is bigger, therefore in will be smaller. We'll be having this particular relationship between in and ik. Okay, now what does this say? Ik is bigger, therefore you have ak, here you have bk, you have in, and here you will be having bn. Therefore we can write from this, we can write ak less than or equal to an less than or equal to bn. See, ak less than or equal to an less than or equal to bn. Okay, see, in both cases, in case 1 and also in case 2, we have the same relation, about ak is less than or equal to bn. Okay, ak is less than or equal to Bn. Therefore, whatever be the value of n and k, therefore we have ak less than or equal to bn for every k. Okay, for every k belong to n. So what does this mean? This means the collection Bn will form an upper bound. Okay, so this implies Bn is an upper bound. Okay, this implies Bn is an upper bound of the set. Bn is an upper bound of the set AK, where k belong to set of all natural numbers. So Bn is an upper bound. But eta is the supremum of n belongs to set of all natural numbers. See, both these sets are actually the same. Here we are just for we have just replaced n and k. Okay, here k is a natural number, here is natural, so both is the same. Here eta is the supremum of this set, and bn is the upper bound of this set. So how do you compare eta and bn? So by the property of supremum is the least upper bound. So this implies eta is less than or equal to bn for every n belong to n. Okay, whatever be the value of n, eta will be less than or equal to bn. Eta is actually less than or equal to b1, less than or equal to b2, less than or equal to b3, etc, etc, etc. Okay. Now you see, now we got eta less than or equal to bn for every n belong to n over here. And previously we have what? Previously we have an less than or equal to eta for every n belong to n. So an less than or equal to eta, and here you have eta less than or equal to bn. So combining these two, we get, combining the two relations, we get, combining the two relations, we get an less than or equal to eta less than or equal to bn for every n belong to set of all natural numbers. Now what does this mean? This implies eta belong to bn for every n belong to n, or this implies eta belong to in for every n belong to n. Okay, so hence proved. So this is the